Picture yourself standing at the edge of everything you've ever known, peering into an abyss so vast that light itself hasn't had time to cross it. Now imagine discovering that this edge isn't really an edge at all. It's just the limit of what you can see, like standing on a ship in the middle of the ocean, where the horizon surrounds you in every direction. This is the mind-bending reality we face when we ask, what's on the other side of the universe? Today, we're embarking on a journey to the very limits of human knowledge, where cutting-edge science meets profound mystery, and where every answer spawns a dozen new questions. If you're fascinated by the biggest questions in cosmology and want to explore the absolute frontiers of human understanding, make sure to subscribe to this channel and give a thumbs up. Now let's begin. To understand what lies beyond the universe, we first need to grasp a fundamental distinction that even many science enthusiasts miss: the difference between the universe and the observable universe. The observable universe is everything we can possibly see or detect, a sphere centered on Earth with a radius of about 46.5 billion light-years. Yes, you heard that correctly. 46.5 billion light-years, even though the universe is only 13.8 billion years old. This seeming paradox occurs because space itself has been expanding while light travels toward us. Imagine you're watching a friend walk away from you on a moving walkway at an airport. They're walking at a normal pace, but the walkway carries them away even faster. Similarly, light from distant galaxies travels toward us at light speed, but the space it moves through keeps expanding, carrying those galaxies even farther away. The most distant objects we can see emitted their light when they were much closer, but they've since been carried away by cosmic expansion. The cosmic microwave background, or CMB, represents our ultimate observational limit. This faint radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964, is the oldest light in the universe, emitted just 380,000 years after the Big Bang, when the universe first became transparent. The Planck satellite, which operated from 2009 to 2013, mapped this ancient light with extraordinary precision, revealing tiny temperature variations that would eventually grow into the galaxies and galaxy clusters we see today. But here's where things get truly strange. The CMB we observe comes from a spherical shell around us, about 46.5 billion light-years away in every direction. This doesn't mean the universe has an edge there. It simply means that's the farthest back in time and space we can observe. It's like being in a thick fog where you can only see a certain distance in every direction. The fog might extend much farther, but your vision has limits. Beyond our observable horizon, the universe almost certainly continues. How can we be so confident? The answer lies in the remarkable uniformity of what we can see. The CMB temperature is nearly identical in all directions, varying by only about 1 part in 100,000. If the universe ended just beyond our observable horizon, we'd expect to see some evidence of this edge, some asymmetry or gradient in the cosmic background radiation. Instead, we see uniformity that strongly suggests the universe extends far beyond what we can observe. The shape of the universe provides more clues about what lies beyond. According to Einstein's general relativity, space can curve in 3 basic ways. It can have positive curvature like a sphere, negative curvature like a saddle, or be flat like an infinite plane. Measurements from the Planck satellite and other observations show that our universe is flat to within 0.4% uncertainty, an extraordinary level of precision. A flat universe could be infinite, extending forever in all directions, or it could be finite but unbounded, like a 3-dimensional version of a cylinder, or torus. In the infinite case, there's literally no other side, just more universe forever. In the finite case, if you could somehow travel faster than light, which physics forbids, you might eventually return to your starting point from the opposite direction, like sailing around Earth. The inflationary model of the universe, first proposed by Alan Guth in 1980, adds another layer to this cosmic mystery. According to inflation theory, the universe underwent a period of exponential expansion in its first fraction of a second, growing by a factor of at least 10 to the 26 in just 10 to the negative 32 seconds. This mind-boggling expansion would have taken any pre-existing irregularities and stretched them far beyond our observable horizon. If inflation occurred as theorized, our observable universe represents only a tiny fraction of the whole. Imagine an ant on a balloon that suddenly inflates to the size of Earth. The ant's visible horizon would encompass only a microscopic fraction of the balloon's surface. Similarly, inflation would have created a universe vastly larger than what we can see. Some calculations suggest the entire universe could be at least 10 to the 23 times larger than the observable universe, though it might be infinite. This brings us to one of the most controversial and fascinating ideas in modern cosmology, the multiverse. If inflation can happen once, why not multiple times? This concept, called eternal inflation, suggests that inflation never completely stops everywhere. Instead, while some regions like our observable universe stop inflating and cool down, other regions continue inflating forever. New pocket universes constantly form as different regions exit inflation at different times, creating an endless fractal structure of universes within universes. Think of it like a pot of boiling water where bubbles constantly form, grow, and pop. Each bubble represents a universe like ours, but the water keeps boiling, creating new bubbles forever. In this scenario, what's beyond our universe isn't just more of the same, it's an infinite collection of other universes, each potentially with different physical properties. The distance between these pocket universes grows exponentially due to the inflating space between them, making them causally disconnected forever. The implications are staggering. In some pocket universes, the fundamental constants might be slightly different. Gravity could be stronger or weaker, atoms might not form, stars might burn differently or not at all. The vast majority of these universes would be sterile and lifeless, but in an infinite multiverse, even incredibly unlikely combinations would occur infinitely many times. There could be universes almost identical to ours with just tiny differences, and others so alien that matter and energy behave in ways we can't imagine. This isn't just wild speculation, it emerges naturally from our best theories of the early universe. The same physics that explains why our universe looks uniform and flat also predicts this eternal inflation and the resulting multiverse. Many physicists find this troubling because it seems to place other universes forever beyond observational reach, pushing science into untestable territory. Others argue that if a theory makes testable predictions about our universe and naturally implies a multiverse, we should take that implication seriously. String theory, another approach to fundamental physics, independently suggests a multiverse. According to string theory, what we perceive as particles are actually tiny vibrating strings in a 10 or 11-dimensional space. The extra dimensions beyond our familiar 3 are thought to be compactified, curled up so small we can't detect them. But there are an enormous number of ways these extra dimensions could be configured, perhaps 10 to the 500 different possibilities, each leading to a universe with different physical laws. This creates what physicists call the landscape of possible universes. Each configuration represents a different valley in this metaphorical landscape, with our universe occupying just one valley among countless others. If eternal inflation populates all these possibilities, then somewhere beyond our cosmic horizon exist universes with every possible set of physical laws allowed by string theory. It's a humbling thought. Our entire universe, with its specific forces and particles, might be just one random example from an unimaginably vast cosmic lottery. But how can we test such ideas when these other universes are forever beyond our reach? Some physicists have proposed that colliding universes might leave detectable signatures in the cosmic microwave background. If our bubble universe bumped into another during inflation, it could create a circular pattern of hot or cold spots in the CMB. Several teams have searched for such collision signatures, analyzing data from the WMAP and Planck satellites. While some intriguing circular patterns have been found, none show the specific characteristics predicted by bubble collision models. Another approach involves the anthropic principle, the observation that our universe's physical constants seem fine-tuned for the existence of stars, planets, and life. The strength of gravity, the mass of the electron, the energy of empty space all have values that allow complex structures to form. Change any of them slightly, and the universe becomes sterile. In a single universe, this fine-tuning seems to require explanation. But in a multiverse where all possible values occur somewhere, it's no surprise we find ourselves in a universe compatible with our existence. The Copernican principle has guided astronomy for centuries, the idea that we don't occupy a special place in the universe. First, Earth wasn't the center of the solar system, then the Sun wasn't the center of the galaxy, then our galaxy was just one among billions. The multiverse extends this principle to its logical conclusion. Even our universe, with its particular laws of physics, isn't special, but one among potentially infinite variations. Yet the observable universe already contains wonders beyond imagination. The James Webb Space Telescope, operational since 2022, has peered deeper into space and time than ever before, revealing galaxies that existed just a few 100 million years after the Big Bang. These ancient galaxies challenge our models. They're more massive and mature than expected, suggesting galaxy formation happened faster than we thought. Every new observation reveals that even our observable universe contains surprises that push the boundaries of current theories. Dark energy adds another layer of mystery to what lies beyond. Discovered in 1998 through observations of distant supernovae, dark energy causes the universe's expansion to accelerate. It comprises about 68% of the universe's energy density, yet we don't know what it is. Is it a property of space itself, Einstein's cosmological constant? Is it a new field that varies over space and time? Or does it indicate our theory of gravity needs modification on cosmic scales? The answer matters for what lies beyond our horizon. If dark energy is truly constant, the universe will expand forever, becoming increasingly cold and empty. Galaxies beyond our local group will eventually disappear beyond our cosmic horizon, carried away by accelerating expansion. But if dark energy varies, the universe's future and what lies beyond our current horizon could be dramatically different. It might even reverse, causing a future contraction, or it could tear the universe apart in a big rip. Dark matter, comprising about 27% of the universe's energy density, presents another cosmic mystery that affects what might lie beyond our observable horizon. We can't see it directly, but its gravitational effects are undeniable, from the rotation of galaxies to the large-scale structure of the cosmic web. The distribution of dark matter extends beyond what we can observe, forming vast cosmic scaffolding upon which visible matter collects like dew on a spider's web. The cosmic web itself is one of the universe's most magnificent structures. Galaxies don't spread randomly through space but concentrate along filaments, creating a foam-like structure with enormous voids between. The Sloan Digital Sky Survey, mapping millions of galaxies since 2000, has revealed this structure in breathtaking detail. The largest filaments stretch over 1 billion light-years, while the biggest voids span hundreds of millions of light-years with almost no galaxies inside them. This cosmic web certainly extends beyond our observable horizon. Computer simulations starting from the tiny fluctuations in the CMB show that gravity naturally creates this web-like structure everywhere. The Millennium simulation and its successors used supercomputers to model how billions of dark matter particles evolve over cosmic time, creating structures that match our observations perfectly. If our physics is correct, similar structures exist far beyond what we can see, possibly extending infinitely. But here's a mind-bending possibility. What if different regions beyond our horizon have different physical properties? Some theories suggest that during inflation, quantum fluctuations could create regions where the Higgs field, which gives particles their mass, settled into different values. In these regions, electrons might be heavier or lighter, atoms might be larger or smaller, and chemistry as we know it might be impossible. These wouldn't be separate universes but distant regions of our own universe with alien physics. The concept challenges our understanding of natural laws. We've always assumed the laws of physics are universal, the same everywhere and everywhen. But maybe they're only locally universal, like how Earth's gravity seems constant to us but actually varies with latitude and altitude. On cosmic scales beyond our horizon, even fundamental constants might vary. Some observations of distant quasars have hinted at tiny variations in the fine structure constant, which determines the strength of electromagnetic interactions, though these results remain controversial. Recent discoveries have pushed the boundaries of what we thought possible, even within our observable universe. The South Pole. Telescope and Atacama Cosmology Telescope have found evidence of enormous structures that seem to violate the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The axis of evil in the CMB, strange alignments of temperature fluctuations, suggests the universe might have a preferred direction, though this could be a statistical fluke or systematic error. The Great Attractor, a gravitational anomaly pulling galaxies toward it at hundreds of kilometers per second, lies partly hidden behind our galaxy's disk. The Shapley supercluster, one of the most massive structures in the observable universe, contains tens of thousands of galaxies in a region hundreds of millions of light-years across. These discoveries remind us that even within our observable horizon, massive structures and phenomena exist that we're only beginning to understand. Quantum mechanics adds another layer of weirdness to cosmological questions. The many-worlds interpretation suggests that every quantum event splits the universe into parallel branches. If true, what lies beyond might include not just more space, but parallel quantum branches where history unfolded differently. These wouldn't be spatially separated, but would exist in the same space in different quantum states, an infinite stack of universes occupying the same cosmic volume. Loop quantum gravity, an approach to unifying general relativity with quantum mechanics, suggests space itself might be discrete at the smallest scales, made of tiny loops about 10 to the negative 35 meters across. If space is fundamentally granular rather than continuous, this could affect the universe's large-scale properties. Some models suggest this quantum foam structure might create a natural boundary to space, though at distances far beyond our observable horizon. The holographic principle, emerging from black hole physics, proposes something even stranger. It suggests that all the information in a volume of space can be encoded on its two-dimensional boundary. Applied to cosmology, this implies our three-dimensional universe might be a projection from information encoded on a distant, two-dimensional surface. What lies beyond might not be more three-dimensional space, but the two-dimensional holographic screen from which our reality projects. This sounds like science fiction, but it emerges from rigorous physics. The ADS-CFT correspondence discovered by Juan Maldacena in 1997 shows that certain gravitational theories in higher dimensions are mathematically equivalent to quantum theories in lower dimensions without gravity. It's like discovering that a three-dimensional hologram and a two-dimensional film are just different ways of encoding the same information. Cosmic strings, if they exist, could provide windows into physics beyond our horizon. These theoretical defects in space-time, thinner than an atom but potentially stretching across the observable universe, would be relics from phase transitions in the early universe. They would gravitationally lens light in distinctive ways, creating double images of distant galaxies. While we haven't definitively detected any cosmic strings, they remain possible, and their properties could tell us about physics in the early universe and potentially beyond our horizon. The Hubble tension, disagreement between different measurements of the universe's expansion rate, might hint at new physics affecting what lies beyond. Measurements using the cosmic microwave background give one value, while measurements using supernovae and other distance indicators give another, higher value. This discrepancy has persisted despite increasingly precise observations. It might indicate that our understanding of cosmic expansion is incomplete, which would affect our models of what lies beyond the observable universe. The concept of cosmic topology introduces fascinating possibilities about what lies beyond. While the universe appears flat on observable scales, it could still have a non-trivial topology, like a flat piece of paper rolled into a cylinder or folded into a torus. In such universes, if you traveled far enough in one direction, you'd eventually return to your starting point. The universe would be finite, but without boundaries, like the surface of a sphere, but in 3 dimensions. Astronomers have searched for evidence of such topology by looking for repeating patterns in the CMB or identical circles from different directions. If the universe was smaller than our observable horizon and had wrapped topology, we'd see the same structures from different angles, like looking in a hall of mirrors. The Planck satellite data shows no such repetitions down to very small scales, suggesting that if the universe does wrap around, it does so on scales larger than our observable horizon. This raises a profound point. The universe could be finite, infinite, or self-connected, and we might never know for certain. Our observations can only constrain possibilities, not determine them, absolutely. It's humbling to realize that such a fundamental question about reality, whether space goes on forever, might be forever unanswerable. The universe guards its ultimate secrets behind horizons we cannot cross. Time adds another dimension to what lies beyond. Due to cosmic expansion, our observable horizon changes over time. We can see galaxies today that future civilizations won't be able to see, as accelerating expansion carries them beyond the horizon. Conversely, there are regions of space we cannot see now that our descendants might observe. The beyond is not static, but dynamic, constantly shifting as the universe evolves. In fact, if dark energy continues its current behavior, the far future universe will look dramatically different. All galaxies beyond our local group will disappear beyond the cosmic horizon. Future astronomers, billions of years from now, might conclude they live in an island universe surrounded by emptiness, unable to detect the cosmic expansion or the CMB. They would have no direct evidence of the Big Bang or the existence of other galaxies. What lies beyond for them would be fundamentally unknowable in ways that our current beyond is not. The possibility of variable fundamental constants adds another layer. Some theories suggest constants like the speed of light or the strength of forces might vary over cosmic scales or time. If true, regions beyond our horizon might have slightly different physics. Stars might burn differently, atoms might be unstable, or entirely new phenomena might exist. The Australian astronomer John Webb has found hints that the fine structure constant might vary across the sky, though these results remain debated. Consider the implications if physical constants do vary. It means that what we call laws of physics might be more like local bylaws, valid in our region but not necessarily universal. The universe beyond our horizon wouldn't just contain more galaxies like ours, but could host phenomena we can't imagine because they're impossible with our local physics. It would be like discovering that mathematics itself changes in different regions, that 2 plus 2 equals 5 somewhere beyond our cosmic horizon. Quantum entanglement might connect us to regions beyond our classical horizon. When particles become entangled, they maintain instantaneous correlations regardless of distance. Some physicists speculate that quantum entanglement from the early universe might still connect particles in our observable universe with particles beyond our horizon. While this wouldn't allow faster-than-light communication, it suggests a deep quantum structure underlying space that transcends classical boundaries. The ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that quantum entanglement and wormholes are fundamentally the same phenomenon described in different languages. If true, every entangled pair of particles is connected by a microscopic wormhole. The universe might be riddled with quantum connections that ignore classical spatial separation. What lies beyond might be quantum mechanically connected to what's here in ways we're only beginning to understand. Cosmic inflation provides one of our best tools for understanding what lies beyond our horizon. The tiny quantum fluctuations in the inflaton field, stretched to cosmic scales, became the seeds of all structure we see today. But inflation would have created similar fluctuations everywhere, including regions beyond our horizon. Statistical analyses of our observable universe thus tell us about the likely properties of regions we cannot see. It's like inferring the entire ocean's properties from studying one random bucketful of seawater. The measure problem in cosmology highlights deep conceptual challenges in thinking about infinity. If the universe is infinite or contains infinite pocket universes, how do we calculate probabilities? Every possible event happens infinitely many times, making traditional probability meaningless. Cosmologists have proposed various measures, ways of counting infinite sets, but no consensus exists. What lies beyond our horizon might not just be physically inaccessible, but mathematically intractable. String theory's landscape problem compounds this issue. With 10 to the 500 possible configurations of extra dimensions and eternal inflation potentially realizing all of them, how do we predict which universe we should observe? Some physicists argue this makes string theory untestable and therefore unscientific. Others suggest we need new ways of thinking about probability and prediction in cosmology. The debate touches on fundamental questions about what science can and cannot address. Recent observations of galaxy clusters have revealed enormous structures that push the boundaries of the cosmological principle. The giant arc, discovered in 2021, spans over 3 billion light-years, about 1/15 of the observable universe's radius. Such large structures challenge our assumption that the universe is homogeneous on the largest scales. If similar or larger structures exist beyond our horizon, the universe might be far more varied and structured than we assume. The cosmic void phenomenon presents another puzzle about what lies beyond. We've discovered voids spanning hundreds of millions of light-years with almost no galaxies inside them. The KBC void in which our local group may reside could be 2 billion light-years across. If such enormous empty regions exist within our observable universe, what unimaginable structures might exist beyond? Perhaps there are voids so vast that entire observable universes could fit inside them, or concentrations of matter so dense they defy our current understanding of structure formation. Computer simulations of cosmic evolution have become incredibly sophisticated. The illustrious TNG project simulated a cube of the universe over 1 billion light-years across, tracking the gravitational interaction of billions of particles over 13.8 billion years. These simulations reproduce the observed properties of galaxies and cosmic structure remarkably well. When we extend these simulations beyond our observable horizon, They suggest more of the same, endless cosmic web stretching infinitely. But simulations assume our physics remains valid, which might not be true in regions we cannot observe. The Sunyaev-Zeldovich effect allows us to detect galaxy clusters through their interaction with the CMB regardless of their distance. As CMB photons pass through hot gas in clusters, they gain energy, creating a distinctive signature. The South Pole Telescope and Atacama Cosmology Telescope have used this effect to find thousands of clusters, some at the edge of our observable universe. This technique might eventually detect structures influenced by physics beyond our horizon, as their gravitational effects pull matter in our observable universe. And have you ever wondered how long it would take to reach the edge of the universe? I talk about that in my video called "This is Why It's Impossible to Reach the Edge of the Universe." In this mind-bending video, we reveal the real science behind the cosmic horizon, the expanding universe, and why the edge of the cosmos is forever out of reach. The link is in the description and pinned on the comments. Consider the philosophical implications of an infinite universe. If space is truly infinite and matter is distributed roughly uniformly, then every possible arrangement of particles must occur somewhere. This means exact copies of you reading these exact words exist infinitely many times throughout the infinite universe. The nearest copy might be about 10 to the 10 to the 29 meters away, a number so large it's meaningless to human comprehension. These wouldn't be different people similar to you, but exact quantum duplicates living identical lives up to this moment. This leads to even stranger implications. In an infinite universe, there would be regions where history unfolded differently, where dinosaurs never went extinct, where humans never evolved, where the laws of probability seem violated because of random fluctuations. Everything that isn't forbidden by the laws of physics must happen somewhere. The universe beyond our horizon wouldn't just contain more galaxies, but every possible story, including ones that seem impossible from our limited perspective. But many physicists find the idea of an infinite universe with infinite copies troubling. It seems to rob our existence of meaning. If everything happens infinitely many times, do our choices matter? This has led some to hope the universe is finite, even if unbounded. Others argue that each region of space-time is unique, regardless of similar patterns elsewhere, preserving the significance of our local experience. The black hole cosmology hypothesis proposes something radical. Our entire universe might exist inside a black hole in a higher dimensional parent universe. The Big Bang would be the formation of this black hole from the parent universe's perspective. What lies beyond our universe would be the interior of the parent universe, forever inaccessible due to the black hole's event horizon. This isn't mainstream cosmology, but it illustrates how creative physicists have become in trying to understand ultimate reality. Observational astronomy continues to push boundaries. The 30-meter telescope and the extremely large telescope, both under construction, will see the first galaxies forming after the Big Bang with unprecedented clarity. They might detect population 3 stars, the universe's first generation, formed from pure hydrogen and helium. These observations will tell us about conditions when our observable universe was much smaller, potentially revealing clues about what lies beyond current horizons. The cosmic infrared background contains all the light from all the stars that ever existed, redshifted and accumulated over cosmic time. It's incredibly faint, but encodes information about star formation throughout cosmic history. Careful analysis might reveal patterns or anomalies hinting at structures beyond our horizon influencing our observable universe through gravity or other forces. Every photon carries information, and we're getting better at decoding these cosmic messages. Fast radio bursts discovered in 2007 remain partially mysterious, These millisecond flashes of radio waves come from distant galaxies, but we don't fully understand their origin. Some appear to repeat, others don't. They might be from magnetars, neutron star mergers, or something entirely unexpected. As we detect more and understand their sources better, they might become probes of the distant universe, revealing conditions in regions approaching our observational limits. The Lyman alpha forest, absorption lines in quasar spectra from intervening hydrogen clouds, maps the distribution of matter along our line of sight to distant objects. As our telescopes improve, we can use more distant quasars as backlights, probing closer to our observational horizon. Patterns in this cosmic forest might reveal whether matter distribution changes near the horizon or remains uniform, constraining what lies beyond. Artificial intelligence is revolutionizing astronomy. Machine learning algorithms can identify patterns in vast datasets that humans would never notice. They've discovered new types of galaxies, identified gravitational lenses, and found patterns in the cosmic web. As we apply AI to larger surveys and more sophisticated simulations, we might discover unexpected patterns that reveal new physics or hint at what lies beyond our current understanding. The interplay between quantum mechanics and cosmology becomes crucial at the universe's boundaries. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire universe. In this framework, the universe doesn't evolve through time. Instead, time emerges from the quantum state. What lies beyond might not be more space or time, but different quantum states, different solutions to the universal wave function that have no classical interpretation. The vacuum energy catastrophe highlights how poorly we understand empty space itself. Quantum field theory predicts that empty space should contain enormous energy from virtual particle fluctuations, about 10 to the 120 times more than we observe. This discrepancy between theory and observation is one of physics' greatest puzzles. If we can't understand the vacuum energy in our observable universe, how can we predict what lies beyond? Perhaps different regions have different vacuum energies, creating a landscape of universes with varying amounts of dark energy. Recent studies of the cosmic optical background, or the visible light from all sources throughout cosmic history, have found more light than expected from known sources. This excess optical background might come from sources we haven't identified yet, possibly from the first stars or from exotic processes in the early universe. These hidden sources might extend beyond our current observational capabilities, suggesting that even within our horizon, significant phenomena remain undiscovered. The lithium problem exemplifies how the universe still surprises us. Big Bang nucleosynthesis predicts how much hydrogen, helium, and lithium formed in the first few minutes after the Big Bang. The predictions match observations perfectly for hydrogen and helium, but we observe only about 1/3 the expected lithium. This discrepancy might indicate new physics in the early universe or processes we don't understand. If we can't fully explain element formation in our observable universe, the chemistry beyond our horizon might be even stranger. Primordial black holes, if they exist, formed in the universe's first second from extreme density fluctuations. They could make up some or all of dark matter. These ancient black holes would carry information about conditions in the very early universe, potentially including regions now beyond our horizon. As they slowly evaporate through Hawking radiation over trillions of years, they might release this information back into the universe, providing a fossil record of physics beyond our current reach. The question of whether space is emergent or fundamental becomes crucial when considering what lies beyond. In loop quantum gravity, space consists of discrete quantum units woven together. In this view, asking what's beyond the universe might be like asking what's north of the North Pole, a category error because space itself doesn't exist independently of the quantum structures that create it. The beyond wouldn't be more space, but the absence of the quantum processes that create spatial geometry. Causal set theory proposes that space-time consists of discrete points connected by causal relationships. The density of these points determines the geometry of space-time. In this framework, what lies beyond our universe might be regions where the causal set has different properties, different densities, different connection patterns, or even breakdown of the causal structure itself. It's a radically different picture where geometry emerges from more fundamental causal relationships. The de Sitter space that our universe is approaching, dominated by dark energy with matter increasingly diluted, has bizarre properties. It has a cosmological horizon beyond which we cannot send or receive signals. This isn't just an observational limit, but a fundamental boundary built into the geometry of de Sitter space. As our universe evolves toward this state, what lies beyond becomes not just unobservable, but causally disconnected, erased from physical reality as far as we're concerned. Some physicists propose that consciousness might play a fundamental role in cosmology. The participatory anthropic principle suggests that conscious observation somehow brings the universe into existence. In this view, what lies beyond our collective observation might be in a quantum superposition of states, not fully real until observed. It's a controversial idea that most physicists reject, but it illustrates how the question of what lies beyond touches on the deepest philosophical issues about the nature of reality. The simulation hypothesis adds another layer of speculation. If our universe is a computer simulation, what lies beyond might simply be regions the simulation hasn't rendered yet, like parts of a video game world that don't exist until a player approaches them. The edge of our observable universe might be the edge of what's being computed. This would explain why we have a cosmic speed limit, the speed of light, and a minimum distance scale, the Planck length. They're the simulation's refresh rate and pixel size. Time crystals, confirmed to exist in 2017, are structures that repeat in time rather than space. They represent a new phase of matter that breaks temporal symmetry. If such exotic phases exist, what other strange forms might matter? Take in regions beyond our horizon. Perhaps there are regions where causality flows differently, where time has multiple dimensions, or where the distinction between space and time breaks down entirely. The neutron-star merger observed in 2017 through both gravitational waves and electromagnetic radiation opened multi-messenger astronomy. As we develop new ways to observe the universe, neutrino telescopes, dark matter detectors, even searches for axions and other hypothetical particles, we might discover that what lies beyond our current horizon has been sending us messages all along, encoded in particles and fields we're just learning to detect. Cosmic rays occasionally reach Earth with energies that seem impossible. The Oh My God particle, detected in 1991, had energy equivalent to a baseball thrown at 60 miles per hour, compressed into a single proton. Such ultra-high energy cosmic rays should lose energy traveling through the CMB, limiting their range to about 100 million light-years. Yet we detect them, suggesting either new physics or sources we don't understand. They might carry information about extreme conditions beyond our normal observations. The axis of evil in the CMB, unexpected alignments in temperature fluctuations, might indicate that our observable universe isn't representative of the whole. If the universe has a preferred direction or unexpected large-scale structure, regions beyond our horizon might be dramatically different from what we observe. The universe might not be the uniform, isotropic place we assume, but might have cosmic currents, vortices, or patterns we can barely glimpse at the edges of our vision. The trans-Planckian problem in cosmology raises fundamental questions about the early universe and what lies beyond. During inflation, quantum fluctuations that were initially smaller than the Planck length, the smallest meaningful distance in physics, were stretched to cosmic scales. But our physics breaks down at the Planck scale, where quantum gravity effects dominate. If we don't understand physics at these scales in our past, how can we extrapolate to regions beyond our horizon? The answer might require a theory of quantum gravity we don't yet possess. Recent observations from the Dark Energy Survey have mapped the distribution of dark matter across billions of light-years using gravitational lensing. The resulting maps show the cosmic web in stunning detail, revealing how dark matter channels guide the flow of ordinary matter into galaxies and clusters. These observations confirm that structure formation follows similar patterns throughout our observable universe, suggesting that the cosmic web likely extends far beyond what we can see, possibly infinitely. The Hubble tension, the disagreement between different measurements of the expansion rate, has only grown stronger with improved observations. Local measurements using supernovae give a value about 9% higher than measurements from the early universe using the CMB. This persistent discrepancy might indicate new physics. Perhaps dark energy changes over time, or maybe there's an extra component to the universe we haven't discovered. Such new physics would fundamentally alter our understanding of what lies beyond our observational horizon. Consider the possibility of mirror universes, regions where a different form of matter dominates, perhaps made of particles that are mirror images of our own. Some theories suggest that mirror matter could interact with our matter only through gravity, making it a dark matter candidate. If mirror matter exists, entire mirror galaxies, stars, and possibly even mirror life could exist beyond our horizon, invisible except for gravitational effects. It would be a parallel reality occupying the same space but barely interacting with our own. The cosmic neutrino background from 1 second after the Big Bang should fill the universe with about 336 neutrinos per cubic centimeter. These relic neutrinos are nearly impossible to detect because they have extremely low energy and rarely interact with matter. But if we could map them as we've mapped the CMB, they would show us the universe at a much earlier time, potentially revealing asymmetries or structures that hint at what lies beyond our current horizon. Monopoles, cosmic strings, and domain walls are topological defects predicted by many theories of the early universe. None have been observed, which is actually informative. Their absence tells us about phase transitions in the early universe and constrains what physics might operate beyond our horizon. If such defects exist beyond our observable universe, they could have dramatic effects on the structure and evolution of those regions, creating cosmic landscapes utterly unlike anything in our observable universe. The possibility of varying dimensions adds another layer of complexity. String theory requires extraspatial dimensions, usually assumed to be compactified at microscopic scales. But what if the number or size of these extra dimensions varies across the universe? Regions beyond our horizon might have different dimensional structures, perhaps areas where extra dimensions are larger, creating effectively higher dimensional spaces where physics operates differently. Gravity might be stronger or weaker, forces might unify differently, and entirely new phenomena might exist. Eternal inflation doesn't just create multiple universes, it creates an infinite hierarchy of them. In this scenario, our universe is a tiny bubble in a vastly larger inflating space, which itself might be a bubble in an even larger inflating space, and so on without end. This fractal structure of nested universes means that beyond has multiple meanings, beyond our horizon, beyond our bubble universe, beyond our parent universe, extending infinitely in a cosmic hierarchy that defies comprehension. The anthropic principle becomes almost unavoidable in such scenarios. If physical constants vary across different regions or universes, we necessarily find ourselves in a region compatible with our existence. But this raises profound questions. Are all possible values realized somewhere? Is there a probability distribution favoring certain values? the answers affect our predictions about what lies beyond. If certain constants are more probable, most of the universe beyond our horizon might be similar to what we observe. If all values are equally likely, most of the universe would be alien and lifeless. Time travel, if possible, might provide a way to observe beyond our current horizon. Closed time-like curves, allowed by general relativity under certain conditions, could let future civilizations travel to the past when the observable universe was smaller, then wait and observe regions that are beyond our current horizon. It's highly speculative and probably impossible, but it illustrates how desperate we are to peek beyond the cosmic veil that limits our vision. The digital physics hypothesis suggests that reality might be discrete and computational at its base. In this view, the universe is essentially a vast computation processing information according to fixed rules. What lies beyond our horizon might be regions the cosmic computer hasn't yet calculated, or perhaps different computational processes entirely. The speed of light would be the rate at which information processing propagates through the cosmic computer, explaining why it's a universal maximum speed. Observations of the integrated Sachs-Wolf effect, where CMB photons gain or lose energy passing through gravitational potentials, provide another probe of the universe's large-scale structure. As photons from the CMB travel through growing or shrinking gravitational wells caused by dark energy's influence, they carry information about the evolving cosmic web. Careful analysis of this effect might reveal whether structures beyond our direct observation influence what we can see through their gravitational effects. The concept of the multiverse has evolved from wild speculation to a natural consequence of our best theories. Level 1 simply extends space beyond our horizon with the same physics. Level 2 includes regions with different effective physical constants. Level 3 encompasses quantum parallel worlds. Level 4 includes all mathematically possible structures. Each level represents a different type of beyond, and remarkably, all emerge from mainstream physics rather than exotic speculation. The challenge isn't whether other universes exist, but whether we can ever observe their effects. Recent studies of supervoids in the cosmic web have revealed puzzling features. The cold spot in the CMB might be caused by an enormous supervoid between us and the last scattering surface. The Boss Great Wall, discovered in 2016, stretches over 1 billion light-years. These structures push against the cosmological principle's assumption of uniformity. If such enormous structures exist within our observable universe, what giants might lurk beyond? Perhaps there are structures so large that our entire observable universe would appear as a tiny fluctuation within them. The cosmic web's filaments contain about half of all ordinary matter, with gas heated to temperatures between 100,000 and 10 million Kelvin. This warm-hot intergalactic medium was only recently observed directly using oxygen absorption lines. The discovery reminds us that even within our observable universe, huge components remained hidden until recently. What other cosmic components might exist beyond our current detection capabilities, both within and beyond our horizon? Pulsar timing arrays are detecting a gravitational wave background, a cosmic hum from countless merging supermassive black holes throughout cosmic history. This background carries information about black hole mergers across the entire observable universe and potentially beyond. As these observations improve, we might detect patterns or anomalies suggesting influences from beyond our horizon, such as gravitational waves from exotic sources or evidence of cosmic structures larger than we can directly observe. The possibility of cosmic phase transitions adds drama to what might lie beyond. Just as water suddenly becomes ice at 0 degrees Celsius, space itself might undergo phase transitions under certain conditions. Different regions beyond our horizon might exist in different phases with dramatically different properties. Perhaps there are regions where electromagnetism and the weak force haven't separated, where atoms can't form, or where entirely different forces operate. The universe might be a patchwork of phases with boundaries where physics dramatically changes. Modified gravity theories like MOND attempt to explain dark matter observations without invoking new particles. While these theories struggle to explain all observations, they raise an important possibility. Perhaps gravity itself behaves differently on cosmic scales or in different regions. Beyond our horizon, gravity might be stronger, weaker, or operate according to different rules entirely. The universe might not have one consistent law of gravity, but a patchwork of gravitational regimes. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. Applied to cosmology, this suggests that regions of the universe under constant observation by their environment might evolve differently than isolated regions. Beyond our horizon might be cosmic territories where quantum effects dominate on large scales because they're isolated from observation, creating macroscopic quantum phenomena we can't imagine. Baryogenesis, the process that created more matter than antimatter in the early universe, remains unexplained. We don't know why the universe has a slight matter preference rather than equal amounts of matter and antimatter. Different regions beyond our horizon might have different matter-antimatter ratios. There could be antimatter galaxies, regions dominated by strange quarks, or areas where the matter-antimatter asymmetry reversed, creating cosmic domains of pure antimatter. The measurement problem in quantum mechanics becomes acute when applied to cosmology. How does the wave function of the universe collapse? Who observes the universe to make it real? Some interpretations suggest that consciousness causes collapse, others that collapse never occurs, and all possibilities remain real in parallel worlds. What lies beyond our horizon might depend fundamentally on how we resolve the measurement problem. Different interpretations lead to radically different pictures of reality beyond our observation. Cosmic natural selection, proposed by Lee Smolin, suggests universes reproduce through black holes, with each black hole creating a baby universe with slightly modified physical constants. Universes that produce many black holes have many descendants, leading to evolution toward black hole production. In this view, what lies beyond includes not just more space, but a genealogy of universes, with our universe being one member of an evolved cosmic ecosystem. The information paradox extends beyond black holes to cosmology itself. If the universe began in a state of low entropy and will end in heat death with maximum entropy, where did the initial order come from? Some suggest our Big Bang was the low entropy byproduct of a process in a parent universe, perhaps the collapse of a black hole. What lies beyond might be the higher entropy parent reality from which our ordered universe emerged. Recent discoveries keep surprising us. The ANITA experiment detected what appeared to be upward-going cosmic rays in Antarctica, suggesting particles that traveled through the entire Earth. While probably experimental error or exotic atmospheric effects, some speculated about parallel universes where time runs backward. While that interpretation is almost certainly wrong, it illustrates how observations at the edge of our capabilities often hint at phenomena beyond current understanding. The cosmic optical background shows twice as much light as known sources can explain. The cosmic infrared background also shows excess emission. These backgrounds integrate light from all sources throughout cosmic history, and the excess might come from sources we haven't identified, perhaps population 3 stars, primordial black holes, or exotic processes. These hidden sources might be common beyond our observational limits, suggesting the universe beyond contains phenomena we haven't imagined. As we approach the end of this cosmic journey, we're left with a profound realization. The question, what's on the other side of the universe, doesn't have a simple answer because it challenges our deepest assumptions about reality itself. The universe might not have sides or edges. It might extend infinitely in all directions, or curve back on itself, or exist as one bubble in an infinite foam of universes. What lies beyond our observational horizon is simultaneously the most distant mystery and potentially the most significant question in all of science. Every major advance in cosmology has revealed a universe larger and stranger than we imagined. Before the 20th century, we thought the Milky Way was the entire universe. Edwin Hubble's discovery in 1923 that spiral nebulae were actually distant galaxies expanded our cosmos by factors of millions. The discovery of cosmic expansion, the CMB, dark matter, and dark energy each revolutionized our understanding. The pattern suggests our current picture, as sophisticated as it seems, might be equally incomplete. The James Webb Space Telescope continues to push boundaries, observing galaxies from when the universe was only 3% its current age. These ancient galaxies are surprisingly massive and mature, challenging our theories of how quickly structures could form. Each such surprise reminds us that even the observable universe contains phenomena we don't fully understand. If we can't completely explain what we can see, how can we confidently predict what lies beyond? Yet we're not completely ignorant. The physics that works here, general relativity, quantum mechanics, thermodynamics, almost certainly operates everywhere our physics has been valid. The laws that govern star formation, galaxy evolution, and cosmic structure likely apply throughout space. Our observable universe probably isn't special or unusual, but representative of conditions throughout the cosmos. What lies beyond is probably, in some sense, more of the same. More galaxies, more clusters, more cosmic web extending perhaps infinitely. But more of the same doesn't mean boring or fully understood. Each galaxy contains billions of stars, potentially trillions of planets, and possibly countless instances of life and intelligence. Each cosmic web filament spans billions of light years, containing more matter than we can comprehend. If this pattern extends infinitely beyond our horizon, the universe contains infinite complexity, infinite stories, infinite possibilities within the framework of physics we know. The possibility that physical constants vary beyond our horizon adds spice to this picture. Perhaps most of the universe is sterile, with constants that don't allow star formation or chemistry. But even if habitable regions are incredibly rare, 1 in a trillion, infinity makes them infinite in number. Somewhere beyond our horizon could be regions where physics permits phenomena we consider impossible, stable super-heavy elements, room temperature superconductors, or exotic states of matter we can't imagine. Consider the poetic symmetry. We began this journey standing at an edge, peering into an abyss. We discovered that edge is an illusion created by light's finite speed and the universe's finite age. We learned that space probably extends far beyond what we can see, possibly infinitely. We're not standing at an edge, but floating in a vast ocean, able to see only as far as the horizon in every direction, with more ocean stretching beyond. The universe doesn't have an other side any more than the surface of an infinite ocean has a far shore. Yet our ignorance about what lies beyond doesn't diminish us, it exalts us. We're cosmic entities made from star stuff, organized by evolution into beings capable of asking questions about the universe's ultimate nature. The atoms in your body were forged in stellar cores over billions of years. The patterns of thought in your brain emerged from billions of years of cosmic and biological evolution. You're not separate from the universe pondering what lies beyond. You're the universe itself contemplating its own boundaries. The fact that regions beyond our horizon exist that we can never observe, that might have different physics, that could contain infinite copies of us or worlds utterly alien should inspire not despair, but wonder. The universe is so vast that we'll never exhaust its mysteries. No matter how much we learn, more remains unknown. This ensures that future generations will always have new frontiers to explore, new questions to ask, new boundaries to push. Perhaps the most profound answer to what lies beyond is this: it doesn't matter as much as what lies within our reach. Our observable universe contains more wonders than humanity could explore in billions of years. We haven't visited the planets in our solar system, haven't sent probes to nearby stars, haven't discovered all the galaxies within our observational capabilities. The universe within our horizon offers unlimited opportunities for exploration, discovery, and understanding. Moreover, what lies beyond shapes what's here through its influence. If the universe is infinite, that affects its topology and evolution. If other universes exist beyond our bubble, that explains the fine-tuning of physical constants through anthropic selection. If physical constants vary, that constrains what processes operated in the early universe. What we can't see directly still leaves fingerprints on what we can observe, making the beyond not merely speculative but scientifically approachable. As we stand on the shore of the cosmic ocean, telescopes pointed at distant galaxies, minds reaching toward ultimate questions, we participate in humanity's grandest adventure. Science isn't just about finding answers, but about asking better questions. What's on the other side of the universe leads to deeper questions about infinity, about the nature of physical laws, about the relationship between mathematics and reality, about whether anything truly exists beyond observation. These questions connect you to every human who ever looked at the stars and wondered. Your curiosity about what lies beyond isn't idle speculation. It's the same impulse that drove ancient astronomers to track planetary motions, that pushed navigators to cross unknown oceans, that inspired scientists to peer ever deeper into space and time. You're part of a cosmic conversation billions of years old, carried out through minds made possible by the very universe we're trying to understand. The universe might extend infinitely in all directions, filled with infinite galaxies and infinite possibilities, or it might be finite but unbounded, curving back on itself through dimensions we can't perceive. It might be one bubble in an infinite foam of universes, or it might be all that exists. We might never know for certain, but the attempt to find out has already taught us more about reality than we could have imagined. What lies on the other side of the universe? Perhaps nothing, perhaps everything, perhaps infinity, perhaps mystery. But one thing is certain. Asking the question makes us more human, more connected to the cosmos, more alive to the wonder of existence. Every observation brings us closer to understanding. Every discovery opens new questions. Every generation pushes the boundaries of knowledge further. Thank you for journeying with me to the very edge of everything we know and beyond. I hope you leave with a deeper appreciation for the magnificent cosmos we inhabit and a renewed sense of wonder at the mysteries that remain. Keep looking up at the stars, keep asking impossible questions, and never forget, you're made of atoms, forged in the hearts of dying stars, assembled by the universe into a being capable of contemplating its own vastness. You're not just in the universe, you are the universe, exploring itself. Until next time, may your curiosity guide you toward ever deeper wonder at the cosmic mystery we call home. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How big is the universe compared to the Milky Way? In this mind-blowing video, we'll take you on a journey from the Milky Way, our home galaxy with hundreds of billions of stars, to the edge of the observable universe, where trillions of galaxies form a cosmic web stretching across billions of light years. See you there.